Hello, you're welcome. So this is another topic. So we are still on energy analysis, but this time around we are looking at energy analysis of a closed system with a moving boundary work. All right. So let me illustrate what that actually means. We treated energy analysis of a closed system, based on of course the first law of thermodynamics of a fixed boundary. Okay, we didn't look at a moving boundary, but now here is a moving boundary. So to illustrate this, so this is a cylinder that has a piston, okay, having a gas inside it. Now you know very well that the gases exert pressure on this cylinder, and the work is done by the gas, which pushes the piston up. Okay, now this particular system is what you see in engine, okay, where uh, heat that is actually supplied to the air inside the cylinder, pushing the cylinder up, and of course there's another external force also compresses the cylinder. There's a kind of up and down movement which actually happen at a very fast rate. Okay, it happened at a very fast rate. So now we are meant to calculate the work that is actually done in this movement, okay, done by the gas, all right, on this piston, all right, pushing it up, and that work is known as boundary work because this is a movable boundary. Work is done to move this movable boundary upward, and there's no way we can actually calculate this work if we are looking at a system that is moving very fast. So the only way we are going to calculate, measure the work, all right, analytically, okay, or measure it with some certain level of accuracy is when we are actually considering a quasi-equilibrium, okay, a quasi-equilibrium source, a quasi-equilibrium process. Of course, you know what this process is a very slow process, okay, so in which the movement is actually very slow. So uh, at each instance, you're going to measure a very tiny, okay, movement of the boundary of the piston. All right, so let's say these are the gas exerting pressure, and here is a very differential movement of the boundary, which is dx, differential movement. Okay, so we can measure this differential movement. So with this differential movement, we can calculate, all right, differential work that is done on the boundary. So dwb, so differential work done on the boundary, and you know work is equal to force times distance, so that's going to be the force times of course the differential distance. All right, and you know that force is equal to pressure times area, because pressure is equal to force all over area, right, if you cross multiply. So we can now have it that the differential work done on the boundary, okay, boundary work, differential boundary work is equal to of course pressure times area multiplied by dx. And you know that area times distance is always volume, okay, area times distance is always volume. So we also have it that the differential work done on the boundary, okay, the differential boundary work is p dv. Okay, so this is just for a differential that is done in this, just in this tiny, all right, movement for this small distance. But remember, the calculation is supposed to be for the entire movement from the beginning. Okay, let's say the movement started from this point 1, okay, to the final point where the, of course, the piston move up to the top of the cylinder. This is point 2. So we have to calculate that. We are not only going to calculate for this differential work, so we have to integrate it for the entire state from state 1 to state 2. Okay, so for us to now calculate the total boundary work, okay, that is actually done, we are going to integrate all the differential work, the work from state 1 to of course state 2, okay, of p dv with respect to v, p dv. Now the question is, how do we integrate pressure with respect to volume? The only way we can integrate pressure with respect to volume is, okay, is basically to express pressure in terms of volume as a function of volume. So pressure is a function of volume. Okay, basically for this to actually work, pressure is always a function of volume. So in that case now, the boundary work now is going to be equal to the integral value from state 1 to state 2. Okay, from point 1 to point 2 of pressure, which of course is a function of volume with respect to dV. So whatever function you have of volume, you put it here, then you now integrate. All right, but a situation where the pressure is actually constant, when the pressure is a constant value, okay, it's constant, then we now have it that the boundary work is going to be equal to the integral value from 1 to 2 of the pressure is now constant. I can now write it as P, it's a constant value with respect to dV. Of course, you know very well that constant can always go behind the integral value. So P integration from 1 to 2 of dV, that is here now is more like 1 dV. Okay, the coefficient here is 1. So if you integrate 1 with respect to V, you have V. So what you have is P, then of course then the integral value of 1 with respect to V is just V, that's 1V. Then you insert the upper limit, the lower limit and the upper limit. Okay, let's say the upper limit is the value of the volume, okay, V2. I call it V2, while the lower limit is the value of volume V1. So that's going to be P multiplied by bracket open V2 minus V1. Okay, so that is what you have when of course the pressure is constant. It's not a function, it has a constant value. All right, or it is also is a change in pressure, but the pressure is not a function of volume. This is what you have. All right, so please take note of this. Now there's a way, okay, that's a way boundary work can be calculated. It can be calculated from a graph, from drawing the graph of the pressure. Okay, so remember, you can draw the graph of the pressure, okay, against the volume. Now in a case where the pressure is constant, let's say the maximum pressure is P. Okay, in the case where the pressure is changing and of course the volume is also changing, so let's say you have this is the graph. So at this point, this is where you have the initial volume. This is a graph of pressure versus volume. All right, pressure versus volume. So this is the initial volume V1. Then at this point, okay, so this is where you have the final volume V2. Okay, so now let's say this is the piston. Okay, this is the piston. This is the piston cylinder. Okay, all right, and here we have okay. So now at this point you take the differential volume dV. So this is the differential volume, okay, so which is taken. Now you discover that for us to be able to calculate the work, as we've already stated the formula, okay, we should actually consider the path through which this the volume actually moves. This is the, see this graph, okay, this is the path, the path of movement from V1 to V2. That doesn't mean that is going to be the only path, okay. So this is the path of movement from V1 to V2. It is also possible for us to have the same graph. Okay, then from V1 to V2, okay, the movement, let's say this one is upward stroke. All right, remember in engine it is actually both expansion and compression. This is expansion. All right, then of course after the expansion the next is going to be a compression. Okay, so compression now is the movement from V2 back to V1. So there's a movement, so there's going to be a movement from V2 back to V1. So this is expansion from V1 to V2. This is compression. Now one thing about compression is this: if the compression also move in the same path, okay, in the same path as this, from V1, from V2 back to V1, then you discover that no work is done, because the work that is done, the boundary work that is done here will cancel the boundary work that was done here. Okay, so at the end of the day, the work is zero. Now, because the work done is not zero, the only way that can actually be possible if the movement, okay, during the compression process move through a different path. So that simply means that it goes like this, back to, this is point 1, this is point 2, okay? So point 1 and point 2. So if we move through a different path. So at the end of the day now, for us to calculate the work, the net work that is done is, when you find the difference, the work that is done for this is actually gotten by evaluating the area under this particular curve, which we calculated by, of course, using integration. Okay, so then of course the work that is done for this is also gotten by calculating the area, all right, under this curve, all the way down the area. So this is, let's say this is A1 and this is A2. So that means the net work now, the net work that is actually done for both the expansion and the compression is going to be equal to A2 minus A1. Okay, the area under the graph. So area under A2 minus A1, because at the end of the day, if you combine these two graphs together, you are going to have a loop. Okay, let me draw that. If you combine the two graphs together, this is one goes through this part. Okay, so then the other, this is point 1 to point 2. So the other move backward, this is the direction from the arrow. Then the other goes in this direction back to where it's starting from to complete the circle. So the work that is actually done at the boundary work becomes the area under this loop. Okay, so that becomes the area, which of course is A2 minus A1. So I hope that is well understood. So let's say a situation where this right here, A2, this is let's say 8 and this is 4. So the net work is going to be 8 minus 4, which is of course that's going to be 4 kilojoule. I hope that is well understood. Okay, so now this actually shows that we can calculate, okay, work by evaluating the area under the graph. So if we have a very simple graph, not a curve, because it is not easy to calculate area of a curve, okay, because curve doesn't give you a specified shape. But for a uniform work that actually give a specified shape. For example, let's say this is pressure, all right, and the the process of expansion actually moves in this such a way that okay, this is the final volume from the origin, okay, and the pressures from the origin to this point is P, and you can see this is actually a triangle. Okay, so the boundary work for this will simply, I don't need to use integration. All I just need to do is to calculate the area of the triangle, which is half base times height. So this is going to be equal to simply half P times V. I hope that is well understood. Now the question is, the work, this boundary work that is done, what is the consequences in engine? All right, in engine. Now, let's say this is okay, your cylinder, okay, your piston cylinder arrangement. Okay, your piston cylinder arrangement. Now, the movement of this piston is such that it will do an external work. So for an engine, it's usually connected to what is known as a crankshaft. So the crankshaft now is what is connected to, let's say, a wheel. Okay, to a wheel. So as the piston moves through and flow, it actually rotates the wheel. So now you discover that the boundary work that is actually done, all right, is this boundary work is going to be equal to the work that is done, first of all, against friction, because this particular piston is actually moving, okay, it's moving against the wall of the cylinder, so there's friction. So the boundary work is going to be a work, the total boundary work is going to be the work against frictional force, friction. Now, as you can see, as the piston moves, it actually compresses A and expands A. Okay, so there's always atmospheric pressure that it has to overcome, all right, for it to move. So that is work that is done on atmospheric pressure, that is WATM. Then finally, okay, that is work that is done for this particular crankshaft. Okay, crankshaft is actually connected to the external wheel or whatever that is being rotated. Okay, so we have three work now. Work, okay, on crankshafts. So the boundary work is equal to this, of course, this work, all right, and the work on atmospheric pressure, of course, can be calculated as the work on atmospheric pressure can be calculated. So let's write it in terms of their integral value. Okay, so from point 1 to point 2, that is work against friction. The work against friction, of course, is going to be force, frictional force. Okay, that of course times distance. So frictional force of friction, okay, times distance. Then for ATM, that is pressure times area. Then for this crank, that's force, okay, on crankshaft. This is force on friction. So all multiplied by dx. Okay, so please take note of that. Okay, so I'm going to stop here for now. We are going to continue in the next video. So see you in the next video. Thank you very much.